that.
Okay.
Ken?
I didn't have a problem with
you're
that, but
here.
I had battery issues with the, or I had servo resetting issues again. So I set it earlier when we did our thing, built it, and then I went back and they are all started wheeling again. I'm like, just did that.
Oh, that's unusual.
Yeah, I had to go
Is-
back and redo it again. So
Okay, and you did it with 1500 for both servos?
Yeah.
Hopefully.
Yep.
Okay. Shall we get started? Let's see here. And can somebody tell me if it looks like I'm recording?
Says you're recording.
Yes, I see the recording dot in the upper left corner. So
Okay.
it says you're
There we
recording.
go. Yes, I see that now. All right. Thank you. Let's see here. Share screen. Okay. Welcome back, everyone. To day 2 of the distance learning with Arduino for ShieldBot with Arduino workshop. Here we all are, and let's go ahead and get started. So today I'm going to do a quick review of some of the important points from the day 1. After that, we'll move on to some robot navigation. And robot navigation will make it possible to do a certain number of coding examples that facilitate learning new concepts. Aside from, distance equals speed times time, which is in the physics engineering realm, we've also got arrays in the computer science area, as well as learning about functions and calling functions and passing parameters. And there's lots of opportunities with navigation to explore those things in code. After that, we will move on to navigating by touch using the Whisker contact switches that I showed you with a video on Monday. So a quick review of the previous session. For homework for the previous session, what you did was follow the instructions starting on page 16 of the book to install and get the software running. I also added links down near the bottom to the video clips I sent you of getting started with CodeBender and Arduino IDE in case you need to get back to those. And then during the workshop, we got to this point where we had, with the exception of the lights that are built as circuits on the BOE Shield, what we did was we connected our servos, connected the battery pack. Before that, we actually connected the Arduino to the BOE Shield. And then we loaded a sketch that told the servos to stay still, but they didn't necessarily stay still until we used a screwdriver to go in there and adjust a potentiometer inside the servo to a setting that made it stay still. After that, hopefully most of you tried out this code example where instead of 1500 here and here, well, here's the 1500. So this is stay still right here. And 1300 is full speed clockwise, 1700 is full speed counterclockwise, and then 1500 should be full stop. We also talked about the linear control region, or the approximately linear control region, which is basically 1300 and 1700 from the code we just looked at are overkill. Your linear control only happens really between 1400 and 1600, with, again, the middle being full stop at 1500. And that's a common thing for students, is if they want to slow down one of the servos because it's moving faster than the other, they might cautiously back from, say, 1300 to 1325, or they might back the left servo off from, say, 1700 to 1650, 1675. None of that will have any apparent effect. So a tip that you can give to your students is show them this graph. If you think they're ready for it. It depends on the grade level. And explain to them, look, 1400 to 1600 is your speed control range. So if you want to start slowing something down, start at, say, 1410 or start at 1590. And then that way you're going to slow your servo down. So that is yesterday in a nutshell. Then you got some homework to put the robot together, since the servos have been centered and are ready to go in, and with the suggestion to actually put it in the put them in the robot in the way that's a little bit more difficult to access, but higher performance, or it's more difficult to access for re-centering the servos, but it's a little bit higher performance and just nicer running with the axles closest to the center of the robot. So does everybody have something that looks like this? I've got a thumbs up. Couple of thumbs up. That's great. One thing to check is we've got the breadboard on the right side of this picture here. And then there's the programming port and the tail wheel on the left side of the picture. So I'd like you all to take a close look and verify that that's the way that your robot is set up. The breadboard, the whiteboard with all the little holes in it, should be roughly between the wheels, the front two drive wheels that are connected to the servos, and then the tail wheel should be on the other end. If you have it backwards, if the breadboard is hovering right over the tail wheel, all you have to do is pop out the 4 screws on the corners and pull it up, give the board a 180-degree turn, then put it back on with those 4 screws. It's very quick, and if you have it that way, I recommend doing that as soon as possible. As in, if you have it the way it's shown in the picture here, great. If you have the board on backwards, unscrew those 4 screws, give the board a half turn and put it back on. Also, forward. This is, I've been referring to the ball that doesn't do any driving as the tail wheel. And this is kind of like a tail dragger, those old biplanes. So forward is, if you imagine yourself maybe sitting on this breadboard here. Can folks see my pointer? Can I get some thumbs on? Yeah, okay, great. So my pointer is visible. So this breadboard right here, imagine you're sitting here with your legs hanging over the front and you're driving. So forward is this way, left turn is going to be that way, right turn and reverse. So try to keep that in mind. And I'll try to be really specific when I say forward and as we move on, but just give me a shout out if you're not sure what we're looking for. By the way, our first test script will be to go forward for a little while and then stop. And so we want to verify that it went towards the breadboard, that it went the forward that's shown on the slide. And if it didn't, probably what happened is that the left and right servo cables are swapped. And so basically unplugging them, putting P12 into P13 and the one that was into P12 into P13 and vice versa will allow you to then hit the reset button and then it will go this forward as opposed to the accidentally backward. A little bit about forward. Forward involves running the servos in opposite direction. So we're looking at the servo's right side here, and forward is facing to the right, and the wheel has to be turning clockwise to achieve forward. Now, looking at the left side of the servo, now forward would be toward our left, and the left wheel has to be turning counterclockwise. So forward will actually be opposite directions, and full speed forward will actually be 1700 full speed counterclockwise for the left servo and 1300 full speed clockwise for the right servo. So if you use these commands and then add delay 3000, then it'll go for 3 seconds. A more severe way to stop the robot, as opposed to repeating these right microseconds.
Don't you have to put it on first? Then
I'm sorry?
put it together first.
Yeah, so the robot should already be assembled. Hello?
Sorry, I was talking to myself.
Oh, okay. Okay, so servo left dot detach and servo right dot detach is a hard way to stop it. You could also just copy the servo left right microsecond 1700, servo right microseconds 1300, paste it down below the delay 3000, and then change these values to both 1500, and that would also stop the robot. Another example we'll do is a little bit of speed control. Remember, I said that 1400 to 1600 is your linear speed range. So if we do 1550 and 1450, that should be half speed forward. And then if you swap those values, it's going to be half speed backwards. And then here's the example of the 1500s to make the robot stop without detaching the servos. So let's go ahead
Andy.
and yes, question.
One quick question for you.
Yeah.
I was playing around with this earlier, and I can make it do the forward 3 seconds and stop. And if I hit the reset, it goes forward 3 seconds and stops again.
Okay.
So no problem there. What I'm curious about is if I detach the USB cable, it goes away. It doesn't do anything. Am I missing something? Because I hit the reset, it doesn't work. I've still got the battery power connected. Does the Arduino lose power when you disconnect the USB?
I think my first thought would be that it's somehow it's possible that your batteries are dead.
Well, no, the batteries are live because it runs.
Well,
Could it be switch 1 and 2, position 1, position 2 for the power?
I'm in position 2 so that it rolls forward, because all I'm
yeah.
doing is if I plug it in to the USB, hit reset, off it goes. If I unplug it, hit reset, nothing happens.
okay, I'm going to try that right now. See if I can repeat your symptoms. Let's see here. Okay, I'm opening. Uh-oh. My screen got scrambled. There's the ShieldBot code examples that I downloaded along with the rest of you for homework. And going into chapter 4, we'll do forward 3 seconds. And it takes the Arduino IDE a minute to open. Here it is. All right. Upload. Okay, so I currently have it plugged in. Now my video feed is going to have a fit when I unplug it. So if I freeze for say 20 seconds, don't be alarmed. Just hang on. I'll be back.
Yeah.
Just about loaded.
I mean, I've got mine where I can show you on the camera right now, but
Sure, that would be fine.
if I hit play, you know, there's the tone, off it goes.
Yeah.
Okay. Unplug. Come on. Unplug. Back up. Hit reset. Nada. Hit reset again. Nothing.
Quick question
Plug
before
it
you do
back.
that. Let's just try unplugging the battery power and then plugging it back in, just out of curiosity. Is it in position 2?
Is the,
No joy.
no lights on at all? It's the batteries. It's powering off the USB port when it's plugged in. It's the batteries.
Yeah, check for a backward battery.
Okay.
Check for, let's see, not all batteries connected.
Okay, yeah, I got it. I just need newer batteries. Not a problem.
Yeah, and then a repeat of that all points bulletin from the previous session. It's really important to unplug the barrel jack when you're done with the Arduino for the day, because otherwise it will continue to draw power. So has everybody tried the, if you haven't already done so, let's make sure that everybody can get their forward 3 seconds script or sketch, pardon me, to run.
Andy, can you hear me?
Yes.
Got a question, kind of related to this. So I know the other day we were looking at, I think it was the left motor, because it's wired to pin 13, which is the LED on the Arduino.
Yeah.
And anytime you start or reset the Arduino, it kind of pulses pin 13, right?
Yes.
It's known.
Yes.
So the problem I have with that is, I mean, I've got BoBots and a lot of projects, and some of the more fun things that we do is to drive your robot through a maze or whatever. And a lot of that requires the robot to be kind of tuned, right? Just correctly.
Yep.
And with the Arduino, every single time we start, the robot is going to kind of get misaligned first.
Mm-hmm.
And then, is there any workaround for that? I mean, it must be a known issue.
It
the only
is.
one I can think of is to wire the servos to pins 10 and 11.
Okay, well, there's the way that I suggest to most people, because it minimizes the management of it, it minimizes classroom management. One, you can tell the students, the more classroom management intensive approach would be what you just suggested, which is to tell your students to move their servo cables over, and then they'll have to change all their scripts so that instead of servo left attached 13 and servo right attached 12, please somebody self-mute whoever's giving me the feedback. Oh, thank you. If it becomes a management issue to continue reminding the students to change from 13 to, say, 11 and 12 to 10. So what I suggest doing first off is explaining to the students, have a delay at the beginning of your program. That's usually taken care of by the speaker, which we haven't played with yet. But if you play a speaker tone at the beginning of the program for 2 seconds, then there's an ample delay during which you can move the 3-position switch from 0 to 2. So you move it to 0 to 2, it twitches, and as it's beeping, you set it down, and then off you go. And so that's the easiest, least classroom management intensive approach, is just to get all the students in the habit of doing that. For some groups, it's a worthwhile experiment to move it to 11 and 10 and do the maintenance. So that is fine too. So those are the 2 ways that we've been explaining to teachers who ask.
Great, thank you.
Sure. Okay, so I would like everybody to, if we go back to the code that we've been using, and I just lost my Arduino IDE. Where did it go? Huh. Well, how about oh, here it is, way over on desktop 4. All right, so file and save as. and then wait for your file browser to come up. And let's rename it forward 3 seconds, half speed. So then what we can do is take this 1700 and change it to 1550. And take the 1300, change it to 1450. And I'd like you all to try that, starting from the pre-written code of forward 3 seconds, and see if it takes your robot forward at roughly half speed. And I'm going to try that here. Let's see.
Yeah, Andy, I notice even with the tone, it'll start moving before the warning, the tone comes on. So I guess for the classroom, I would just have them, you know, if we are checking it, hold it up, put it down when you hear the tone.
Well, yeah, basically you have to wait for the tone to start.
Understood, but the movement is occurring before the tone even happens.
Yes,
At
and
least
so
on
you
mine it is.
want to be holding it.
Yeah.
Turn the switch from 0 to 2.
Yep.
It'll twitch. The tone will start playing, and that's when you want to set it down.
Put it
And
down.
so that's the instructions that just to make life easiest to give to the students. And here also you can take that tone. So this number is the speaker pin. This is the frequency, and this is the duration. So you could actually change that duration to say 2 seconds or 3 seconds, whatever's ample for giving the students enough time to set it down. Yeah, thanks for asking. That's a really good point. Okay, how are we doing? Has everybody got their slowly moving robot? What do you get if you try 25 and 75? So 1525 and 1475. So question is running robots tethered via USB a viable option? I have done this with another robot. Yes, you still need to have the batteries in. It's true that the robot, like we saw a case today where the robot did run, even though the batteries were there was something not connected in the batteries. And by the way, whoever was wrestling with that, if you try new batteries and it fixed everything, great. Otherwise, try unplugging check to make sure that the battery cable is firmly plugged into the Arduino. If it's just partially plugged in, it might be hanging on and behaving like it's plugged, but if it's not all the way sunk in, it might not be supplying the power. So that would be another thing to look at.
I was the guilty party, and a fresh set of batteries took care of it.
Oh, excellent. Okay. And yeah,
So, there you go.
third time, everybody remember to have yourself and your students unplug that barrel jack, unplug that barrel plug from the barrel jack on the Arduino when you're done for the day, because otherwise it will continue to drink a small amount of current all night or all week, and that can cause difficulties with the batteries. By the way, rechargeable and alkaline are fine. I recommend high capacity rechargeable batteries. I'll try to remember to show you a link on Friday for a nice one that I've been really happy with using in my robots by Tenergy, nickel metal hydride batteries that have new technology so they don't self-discharge as quickly as nickel metal hydride had a reputation for earlier on. Okay, so how are we doing here? Let's please feel free to just jump in if you want to ask any more questions. That's great. So here we have this full speed forward routine, except for right now I'm at quarter speed forward. Let's also try quarter speed backward. So one quick way of doing that is simply to copy this routine right here that I have shaded and then paste it down below. Then we can adjust it to backwards. Would anybody like to hazard to guess what backward is going to be?
Interchange right and left.
Exactly. So we want to change this. We want to set what used to be the left speed to the right speed. And we want to set what used to be the right speed to the left speed. Another way to do that is to say swap the speeds. And that should have our forward and backward. And just pick a nice speed that's slow enough for your table. So I'm going to do 1530 and 1470.
Unplug this panel. And this is going to go on.
That's a little bit slow, I'd say. I've definitely got, I think I'm going to up mine to say 40 and 60.
Pretty sweet.
All right.
I can't jump ahead. The wheels attached. Okay, so I can't do that until I do this. So I'm just way behind.
Okay, so is there anything I can help you with, whoever is way behind?
I just have to spend some time, sorry.
Oh, okay, that's fine. We can also, we'll have the YouTube video of this posted. Last time, I think it was about 4 hours after the course ended, 4 or 5 hours after the course ended, the session ended, we had the YouTube video up and an email out with the link. So that's one thing. And also we can arrange a catch-up Zoom meeting if you want, that's fine too. What I'd also like to do here is experiment a little bit with left and right. It's hard to remember, but to turn left, remembering the numbers and counterclockwise and clockwise comes from going through each activity in the book. And so as we're skipping through like we are during the workshop, what I'm going to do is call it out. Basically, the left wheel needs to be going clockwise, and so does the right. And so for quarter speed right, and this is rotate in place right, kind of like if you have a robotic vacuum cleaner or a riding lawnmower, those are two things that will do it a similar way. Whoopsie. Okay, so by using the copy and paste method of coding here, I've made several copies of the routine and then adjusted the servo speeds for each one. And so let's wait for everybody to get to this point and to run it and make sure that their robot does in fact go forward, backward, left, and then rotate in place left, then rotate in place right. My challenge for any of you who are patiently waiting would be to try more routines. For example, you could make it pivot on one wheel or pivot on the other wheel. So pivoting left, pivoting right, where one wheel stops and the other goes forward. And then another interesting maneuver is the curve. And all you really need for that is one wheel speed to be somewhat less than the other. And the smaller of a fraction the left wheel speed is of the right wheel speed, the tighter the curve. You can use that to go in circles and other fun things. One of the nice things about the speaker is you get some audio feedback from the attendees, which in your case will be your students, on how they're doing with the testing of their robot.
Susie, could you give me the numbers for left and right turns? I really can't see that on my screen.
Okay, so the numbers for left are 1460, 1460.
1460, 1460. Okay.
Yeah, and then the numbers for right are 1540, 1540. And let's see here. Maybe I can go up to 36.
And what is the reason for that numbering again? Is there like a mathematical something to remember, or?
Yeah, yeah. Stop is okay. So there's a sequence of things. Okay, so the first is that full stop is 1500. That's what we did with our calibration. Can you see on my screen where I'm showing you 1500 is zero speed? See that? And so the other thing is that both wheels have to, if to go forward, both wheels have to be turning opposite directions. So going back to our speed graph, if you want one wheel to turn one direction, you're going to go a certain amount above 1500. Like for half speed, you'd go to about 1550. The other wheel would go 50 below 1400. So that would be 1450. So it's the relationship of that argument in that argument here is here we're 40 above 1500 and here we're 40 below 1500. Do you see that? Okay, good deal. Was that Andrea who asked? Okay, excellent.
Well, is there any special reason for 1500? Could we have picked like say 800 and then just gone like had 800 as our stop and then gone like 850 and 750? Is there a reason why 1500 is the number?
Yes, it goes back to the days of model airplanes. These servos are modified versions. I'm just going to put in full stop for the sake of discussion right here. Okay, so this is 1500, 1500. So that's full stop. I'll just do that for milliseconds, I guess. Okay. The way that servos on model airplanes are controlled is there's a transmitter and it sends radio bursts at a particular frequency. At least the old school ones did. It's gotten to be a little bit more elaborate now, but these are an older model of servo that takes a nice simple protocol where basically the amount of time that the radio burst lasted would cause a standard servo which is the kind of servo that turns to and holds a position to position, say, an airplane flap or a boat rudder, those would expect these radio bursts from your, from the controller that you're holding in your hand and you're operating its thumbsticks. And that would go to the airplane. And depending on how you adjust the thumbsticks, the series of radio bursts that was repeating 50 times a second would last longer or shorter. And that would, and so the servo, the receiver, the radio receiver on the airplane basically would take those radio bursts and convert them to high-low signals that it sent to the servo. And then the servo was designed to say, okay, well, I'm at 1500. That's basically 90 degrees for me. I'm going to turn to and hold the 90-degree position. Oh, wow. Here's 1460. That's going to be basically 60 tenths of a degree clockwise. Let's make it easier. For standard servos, well, I'm just going to throw out a number that doesn't make any sense, but basically it would respond to this by taking a position that's clockwise. It were of 90 degrees by a little ways, 60 tenths, so about 6 degrees. It would respond to this by taking a position that's about 6 degrees counterclockwise of 90 degrees. And it turns to and holds that position. Well, what we did to create continuous rotation servos is we took the same servo and just took the feedback mechanism out that lets it know where it turned to. And so what happens is when you send it this digital signal that it used to receive on an airplane from a radio demodulator, and then come as those 50 pulses per second digital signals, the servo doesn't have its feedback mechanism in there, so it never knows that it's reached 6 degrees counterclockwise of 90 degrees. So the motor keeps turning. And so that's the history behind that. And so it's true that you could somewhat adjust it. You could probably adjust your potentiometer. Like if you decided to set these 1500s to say 1520, that would probably work. But things are going to get a little weird if you go very far above or below 1500 for that center position, because it'll affect the speed of the servo in a particular direction and how it responds. All right, I hope that was a, does anybody want clarification on that? Or hopefully it made sense. I didn't have any visual aids for model airplane theory. I didn't think it was gonna come up. Well, okay, in the absence of further questions, let's move on. So these are the full speed versions of the basic maneuvers. And so you can do this on your floor, for example. And what I'd like you to notice is that we've got this 600 here for turn left in place as a delay. So if we think through this code, servo left, right microsecond 1700, that's full speed, left wheel, counterclockwise. And then this is full speed, right wheel, clockwise. The delay keeps that happening for 2 seconds up until it hits these next two servo pulse statements. And then both wheels turn to make the robot rotate left in place at full speed, but only for 1/6 of a second. Does everybody see how that's working? And then right for 1/6 of a second, and then backwards for 2 seconds. So I'd like you to try that. The name of that code example is forward, left, right, backward.ino. So we'll save what we've got here and then file open, and then go spelunking in your chapter 4 pre-written code for forward, left, right, backward. It's the third folder. And here is
Pretty cool.
yeah. And now we are at a place where we've been writing some fairly inefficient code to do stuff. And it's kind of nice, actually, to, at this point, let the students have a contest, and their code gets kind of large because they're basically copying and pasting. But let's talk about ways to encourage the students to learn more coding techniques so that they're so that they have more control over their program with less work. So instead of saying, gee, let's copy and paste this and then change the parameters, here's some cool things you can do. First of all, try this program as written, then secret technique, you can say /*. I'm going to add a /* right here to make everything below it go away. But I don't want everything below it to go away. A little further down, above, between the delay 2000 and the servo detach, I'm going to add
Old school Unix.
Oh, is that really it? Because it is just a C language.
Yep, old school.
Yeah.
Old school.
it's a C language way of commenting out a block of code. That is to say, we're making the compiler ignore this block of code right here.
Do you need to do that in and out?
Yes, because otherwise it won't even see that you have a loop or the servo detaches at the end. So basically, our turn right and full speed backward, we're going to get rid of those after testing it. Of course, we're going to get rid of those by adding /* above turn right in place, and then */ between delay 2000 and servo detach. When we do that, all we want to see is our robot moving forward and then turning to the left. And if you want it for desktop space, you can reduce the forward to whatever you want. Like I'll make mine 1500. But the 600 we're going to tune to try to get it to do a 90-degree right. Whoops, a 90-degree left. And it looks like for mine only went about 60 degrees. So literally, if I change this to 900, it'll probably give me a good sharp 90-degree left turn. That will vary depending on your batteries.
But that's where you do the assignments with the students, and you
Yes.
graph out what time it takes to do so many degrees.
Well, in this case, instead of degrees of wheel turning, we're talking about degrees of robot turning. And yes, it's great to have them graph it out. I don't know that I specifically have them graphing it as an assignment in the book, but it's a great assignment. Okay, so 90 was just a little high. I'm going to do maybe 880. And don't worry about exact precision. Close enough is fine. You know, say, oh, that's pretty close to 90 degrees. I'm happy. We'll move on. Okay. So mine was just pretty close to 90 degrees. And
Quick question on the calculating this. So those other servos, does that give us more precision to actually calculate wheel turns? Is that either just like, I remember seeing somewhere there were some other servos we could get or something?
well, yeah, like the Feedback 360 servo is a product that comes with the Activity Bot. The Activity Bot also has a propeller microcontroller, which is it has a lot more processing power, and so it's able to do a lot more with the Feedback 360 servos. That's kind of the Arduino doesn't work great with the Feedback 360 servos. It's an older processor that has some shortcomings, both in the amount of code it can run, the speed it can run the code, and et cetera, that there just is not really very well compatible with the Feedback 360 servos. So I'd definitely be looking at the Activity Bot. And then that comes with Feedback 360 servos. And also it's programmed in C, which is kind of the subset of, it's kind of like the common foundation that went into C++. It's so that the syntax is very similar in the Activity Bot. And it's actually, C is more fundamental and then C++. And so a lot of languages branched out from it. So what I wanted to suggest is right now we have, so here's an example of something that the students could do. I don't remember if I specifically assigned this one, but you can, first of all, shade this full speed forward and turn left in place and hit the tab once just to move it all in. Then go above it and say for int n equals 0. We'll count from 1 this time. N equals 1. N is less than or equal 4 n plus plus. Next line, opening curly brace. Then down at the end, we want to have a closing curly brace. And what this is going to do is it's going to cause your robot to go forward and then hang a left. And it'll do that 4 times because this is the same code that we used to count to 10 in the homework and that we discussed on Monday, where basically instead of counting to 10 and knowing that we went through the loop 10 times, what we're doing here is just setting it up so that these 2 maneuvers occur 4 times. And so that should roughly give you a box. And then students love contests. So the first robot to circumnavigate the legs on one of the chairs in the classroom by drawing a box is a quick little contest that you can throw out. And then if they use a loop as opposed to copied and pasted code, you know, style points can be awarded for that if programming is one of the goals of the class. Okay, so let's see. I need to take a vote here about how many of you are getting through that. Okay. Can everybody go to their reactions tab and give me either a thumbs up or a green check if you're done? Okay. Keep going. Let's see those thumbs up, and then give me a thumbs down, of course, if you're still working on it.
Any other question?
Yeah.
Can you use I have a bunch of the old encoders, okay? Can they be, has anyone tried using those with this, or is it just this doesn't have the processing power?
Well, the old encoders, it can probably do, because those encoders are you referring to the encoder kit we made for the basic stamp Bobot?
Yeah.
All right. That encoder kit is doable with the Arduino. I just don't know that there's any code that's been pre-written for it. You might have to do some searches there. Otherwise, it would probably be kind of like looking at the PBasic code and porting it to the Arduino. All right, so looks like we're doing good here. So I'm going to go through some of the other stuff that that the navigation chapter talks about, but we're not going to do all of it. I'm just going to hit it as talking points. So we already talked about testing the speed and slowing down. So one thing that students will find is, well, gee, it curves a little bit to the left or it curves a little bit to the right. And so the idea is that whichever servo is faster, because they're both going at full speed during this 10-second test. And you'll be able to observe that it curves to the left or right. Well, if it curves to the right, both wheels are going full speed. So speeding the right wheel up to straighten it out is not an option. We have to slow the left wheel down. And so this 1700 here, remember that your first step would just be cutting it back to like 1600. And then go 10 at a time from there until it's slowed down and then maybe up by 5. Does that make sense? We okay with that? Got some head nods? Good. Stop me if I'm, stop me if I'm rolling too fast here. I have, of course, a goal about how far to get today. So there's some desire to move quickly through some of this. Using math to go a particular distance. That's another really good one for, and this is chapter 4, activity 4, where we start by saying, okay, let's go forward for a second and see how far we went. Oh, 9 inches. And then use that to figure out and be able to calculate, okay, well, if I want to go 30 inches, we can use some algebra to figure that out. That's another nice activity. And the algebra, by the way, is figuring out how long that delay has to be. So if full speed takes you 9 inches and you want to go 8, full speed at 1 second takes you 9 inches and you want to go 18 inches, well, make it delay 2000 before adding statements that make it stop. That would be the, shooting from the hip approach, but you can come up with some problems that require algebra to get the right answer, and then they can test it, try it out. More coding lessons. The first one is functions. And so this is an example of a function call. And so right down here where it says void example, that's below void loop and void setup. Void example is a user written function that we're just sticking down below void loop. And so inside its curly braces, you have to say void example and then parentheses, opening curly brace, your code, closing curly brace. And inside there, your code can say something in this case. That's usually the quickest way to do it, is to run a code example where up here in setup, it says, hey, we're before the function call. Then here is the function call example. And what example does in this case is it says, hey, sketch, go find the example function, do what's there, and then come back when you're done. So it goes, finds the example function, says prints during function call. When it's done, it comes back to the next command, and then your program moves on normally.
Andy, will it let us do the traditional C format where you have all the functions are up at the top, subroutines, functions all up at the top, and then just have it come down to the setup at which it launches, or is it going to have a problem if those things are up at the top? My gut is
I
it's
thought
wrong
I
because it's got-
tested it and it'll let you do that. So, okay, so down below here, I'm going to add, or no, actually, let me open that example. Up. Oh, what was the name of that?
So in traditional C, you need to have a prototype function above and then the function below, you mean?
Yeah, that's what we're going towards is as he said, in traditional C, you need to have the function prototype above and then the function below, or you just put your main code below all the functions, which is the most common way. However,
in Arduino, it doesn't matter.
Okay, so in Arduino, what they do is they declare the function prototype for you, but don't show you that it happened. They take care of that step. And so my point of curiosity is, well, if I declare it again, I don't think there's going to be a problem, but I wasn't 100% sure about that. Function call with parameter. So this is actually, I haven't talked about it yet, but okay, good. So here we are. And so if I want to declare a function prototype, what I need to do is up here, add the function prototype and follow it with a semicolon. And so if this compiles,
that's what I'm used to.
Yeah. And so that should still be okay. And it's compiling right now, and it hasn't complained at me any. Still compiling. And there we go. Okay, yep. So I'm sorry, whoever said that. You're absolutely right that it does work. I just wanted to test it and make sure myself. And I encourage that, set up a hypothesis and then have your students put it to the test if it's a question. Okay, so the next one in the book, once they learn how to write a function, what you can do is you can write functions that do different pre-programmed maneuvers, which is nice for navigation contests, and it's a nice first step. The book does not really try to open up the fire hose with information. So we say, okay, well, here's how to write a function that doesn't take any parameters. All right, here's how to use that with the robot. Look what it did. And so let's see, where is that? So movements with simple functions, I believe, is the code example to try. And I am pretty sure that all it does is the familiar forward, left, right, backward maneuver. And I guess that I did at this point, I'd have to look it up in the book, but I thought we were doing functions that had pre-written times first, but that may not be the case. So let me briefly talk about that. In this case, this is an example of a function on the next slide here, slide 58, if anybody's following along in the slideshow, where we made a function named pitch. And that function takes a frequency parameter, and then it gives us a speaker tone. So function call with parameter is one you can open and try, and you should get two different pitches, because notice that there's a pitch function call at the start, And then there's a delay and then a second pitch function call where it's a lower pitch because the frequency is lower. Both of those values, when the function call is made, instead of just jumping down, it also passes this value into the function where we have this little variable declared named hertz. And then HZ it ends up in our tone right there. And it ends up printed. It's a pretty cool program. Let's try this one. So function call with parameter. Page 121 in the book. Looking it up real quick to make sure that yeah, function call with parameter is the name of the sketch. So here is function call with parameter. And we'll give it a try. And this one, you can use the serial monitor also. So as soon as you see that it's done loading, try opening the serial monitor. So does everybody have their audio off? Is that why I cannot hear the higher tone and then the lower tone? It would make sense.
I don't have a tone.
Okay. I just let's see. I'm going to open my serial monitor. I just wired up my speaker.
I've just been nice and having mine on mute.
Yeah, thank you.
Can you hear it now?
That was not quite was that audibly two different tones?
Yes, it was.
Ed's laughing, but I don't know why. Unmute yourself, Ed.
I'm sorry, I'm hearing so many tones come that I don't know if I'm listening to your robot or my robot.
Okay.
And that's why I'm laughing.
Sorry about that.
No, it's okay. Because I'm just wondering, gee, this is really loud, but no, it's really low. It's really loud. Okay, not a problem.
Here we go. Here's mine. So that's what it should sound like. And again, what this is it's a demonstration of a function that has a parameter and how it can do various things. It can, it can display that parameter, and it can also do something that affects a speaker with that parameter. And for some reason, there we are. Yeah, pardon me, on my end, I'm not able to get to my serial monitor. Let's try now. Okay. So each time I pressed and released the reset, each time it entered the function, it displayed the frequency. So that is function calls. And so here is an example of our forward, left, right, backward. Instead of one tall program, I split it into two halves. So this is the top and this is the bottom half of the program. And it's not the cleanest coding technique, but it's a nice step to having students get used to calling functions. And so here we have gone through and given each function a name, and it accepts a time to execute each maneuver, be it forward, turn left, right, backward, etc. Now, after that, what we do is we show them, got ahead of myself here. This, I'm going to move this slide because it's not supposed to be here. Oh, no, maybe it is. Okay, sorry. So this is a function with several parameters. So this maneuver function down here, the two functions that get used most in the book is this one for pre-programmed forward, left, right, and backward. And then this other one where we have a maneuver function, and you can give it a left speed, a right speed, and a run time for the maneuver. And one nice thing about this is that you don't have to, it also deals with the reversal. So like full speed forward is 200, 200. We don't have to say positive 200, negative 200 anymore. We can just say 200, 200. And what happens is that the function has code in it that takes care of that for us. And it's actually right in here, the 1500 plus speed left and the 1500 minus speed right is where it does that for us. So this is kind of the culmination of writing functions. Then we go into playing some music, which I'm going to show you because we need to play some catch up in order to get through the whiskers. So we talk about musical notes. And then we introduce arrays. And for those of you who have not used arrays before, an array is simply a list of values. And for example, here's note 0, note 1, note 2. This is the way to access the values in the note array. So if you want to access the note that is, let's see, A, B, C, I believe that's a D note. 1397 use note of 3. And so the students get to try that out, accessing different notes, and they type a different value in there and get a different note. And then after that, they get to revisit the for loop yet again. And it's a really important code block. So here we are with our index again. And this plays solfege, the do, re, mi, fa, sol, la, ti, do, which you'll thank me for not having tried to sing. And so this is another application of arrays. And then at the very end of the chapter, what they do is they combine the using of the maneuver function with 3 different arrays. And then they have a for loop that goes and it grabs 200, 200, 2000, sticks 200, 200, 2000 there. Next time through, the index increases. So it goes and it gets the next set of values, which is negative 200, positive 200, 600. And it goes through each of these maneuvers and we get that same old forward, left, right, backward maneuver that they did earlier. After that, there's lots of questions, exercises, and projects in the back of the book, and some fun things like drawing a circle and a triangle. And with that, are there any questions? Because we're about ready to move on to whiskers. We're good? Thumbs up. All right, let's go. Whiskers. These are the contact switches. It's the first example of navigation with sensor feedback. So on page, bear with me. Okay, on page 148 is going to be your parts that we'll want you to gather. On page 149, it shows how to put those together on the front of the robot. You're going to use the long screw through a nylon washer, then hook the whisker around the screw, through the spacer, and then down in through the front standoff. And then notice that one whisker will go below the nylon washer and the other whisker will go above the nylon washer. This is a front view. Here is the top view. And there's some circuit parts you're going to need too. And those are listed on page, it's going to be right by 150. Okay, on page 148, oh, it does show the resistors. It just doesn't show them in color in your book. So in the parts list, it calls out red, red, brown as the color code for your 220 ohm resistors. And it calls out brown, black, orange as the color code for the 10 kilo ohm or 10,000 ohm resistors. And there are actually 4 stripes. So it's actually red, red, brown, gold, where gold is the 5% accuracy level. And then brown, black, orange, gold. It's not important here, but it will be important later on. So try to make sure you can differentiate between brown, black, gold and brown, black, red. Brown, black, red is 1,000 ohms or 1 kilo ohm, and brown, black, orange is 10,000 ohms or 10 kilo ohms. And like I said, if you made that mistake here and use brown, black, reds, sure, it'll still work. But coming up in another activity, if you accidentally use brown, black, orange when you're supposed to be using, when it's calling out for brown, black, red, you and or your students will have a robot that might seem like it's blind in one or both eyes. I think I'll leave this. So basically what we want to do is have you go through the checklist instructions on 148 through 150. And then display whisker states is what you'll want to run after that. And I'm going to build my whiskers with you guys. And please, anybody yell out if you have a question. Get my camera on here. How's that for larger than life? Okay, so I'm looking for red, red, brown and brown, black, red resistors. So here's the whiskers.
Sorry, really quick question. You keep saying
Yes.
brown, black, red, but the book says brown, black, orange.
Yeah, that was my bad. Brown, black, orange, please.
Sorry.
And no, as a matter of fact, that's really the best thing is that you and hopefully your students will pay close attention to that. It turns out not to matter in this activity, but later on when we do infrared detection, if you accidentally use brown, black, orange when you're supposed to be using either brown, black, red or red, black, red, the detector will become unusefully nearsighted because the light will be so much dimmer because the resistance against current flow will be so much higher.
Will we need to get additional resistors? Because it looks like, at least in the kit, I'm not seeing a brown, black, red. at all?
You will have 3 small bags of resistors. And in one of them, yeah, then they go, so that there's going to be one bag that has most.
I got you. No, I'm just an idiot and couldn't find the last bag. Sorry. Thank you.
It's, yeah, not to worry at all. Because basically, I cannot remember a class where that question hasn't come up. And a lot of that has to do with the fact that because this is kind of a survey course here, we're not going through the book step by step. And so we're not actually taking an inventory of the parts, which is one of the very first activities in the book that, you know, the students can do, because presumably they will have more class hours than we have here in this 6-hour session. Nylon washers. Don't worry, if you have 3 nylon washers, you only need 2 for this activity. Nice long 1-inch screws. And I believe 1/2-inch standoffs that are metal. Okay, so hope you folks are doing okay. If you need to look up just to see all the parts on the camera, there they are.
So a question about the little header pins that you're supposed to put in to.
Oh, actually, yeah, I forgot those.
So, but where do we put them? I mean, do we, because the diagram on the instructions, I think it says something like 7 and 5, but if you look at the diagram, it's more like 6 and 9 or. I don't know.
Yeah, no, I'll go to that in just a second. Let's make sure we know that for sure here.
These have to, like the red, the brown, black, orange have to connect with those header pins, right?
Yes. Actually, we're using all 5 sockets in a row. Can you see my screen okay?
Yeah.
All
Yeah,
right.
that's from the book, right?
Yes. And so 1, 2, 3, 4, 5, 6 down from the top.
Okay.
And then 7, 8, and really, and 9 down from the top.
Okay.
Another way to think about it is you want to make sure if you push on the whisker that it'll make contact with the posts. So like this left whisker will make contact with the post that is connected to digital 5 over here. I sure hope I gave you the right advice a minute ago. I just took it myself and oh, look at that. Okay, so if anybody wants to look up, they can see what we're trying to accomplish here. See how I'm rotating that whisker and it bumps into the post? That's an electrical contact we'll need to discover that the whisker is pressed. So you want to have the screw tightened so that it's holding the whisker a little ways away from the posts of the 3-pin header. And then if you push the whisker in this direction, it should bump into the frontmost post on the 3-pin header. Okay, so when you've got it tightened, this is probably a good distance. You can see what I'm doing here. And it takes a little bit of trial and error to get it so that you've got the screw that's holding the whisker to the post tight and it's still the correct distance, which is about a screwdriver width. Shame on me, I didn't, announce that you're supposed to turn off and unplug all your power, but really for this, we don't need to worry about it. But as a student habit, especially if it's a technical type of school, it'll be important that they get used to that. Oh, 5 volts. Plugged it into the wrong supply. Seven and 5. P7 and P5. For the 220 ohm resistors. All right, let's see.
That's all right. A little behind. Nothing. And this goes into ground. He's there, they're quiet. Oh,
The test code for this is going to be in chapter 5, and it's called display whisker states. And go ahead and just give me an audio or chat shout out when you're or actually, yeah, just chat me when your whiskers are ready for testing so that I know how many of you are ready to test. All right. We have 3 ready.
I'm ready, Andy.
Okay, thank you. So the thing to do is to go into chapter 5 and grab display whisker states and load that sketch in, and then open the serial monitor, i.e. the serial terminal for the Arduino. And then you'll want to be able to see, I believe, 1.1 when the instructions are on page slightly above 150. Feel free to call out anybody. 152 is where the examples and the name of the sketch, which is display whisker states. And again, that's in the chapter 5 of the examples folder you unzipped. So I have that opened and I'm loading it, and we'll soon drag the terminal up so that it covers the back half of the robot. Well, that's not the right program. I'm not able to communicate with my bot, but we'll try later. Okay. And then please get with me if you need to. One thing to try is, if you were able to communicate with your bot earlier and you're not able to communicate with it now, would be to, okay, and then it looks like 1 or 2 of you are going to have to drop out a little earlier than the 4 o'clock time. I will go ahead and send homework, so that should be fine. And then feel free to hit me up with questions, or just check the YouTube video for the last little bit of it, because I'm hoping on talking about the homework a little bit. We shall see.
So just so I'm making sure I'm getting the right display, it's polling, it seems 1111. If I touch the whisker on the right, it drops down to 10, and the whisker on the left looks like it gives me a 0-1. Does that sound right?
Yeah, so can you see my screen?
Yeah.
I'll go ahead and match you on that. So we were talking 1111. That's actually binary 1, binary 1.
Oh, so it's 1-1?
Yeah,
Okay.
1-1. And then if I push on the right whisker,
Right.
now the right digit is 0. So it's 1,
I'm
0.
getting 1-0. Okay.
Yep. And then if I push on the left whisker,
0-1. Okay.
you got it. And guess what? If you push both whiskers and hold.
0-0. Okay.
All right. So you are then ready to try the next sketch.
The navigation?
Yes.
Okay.
And that's on page 156, and the name of, sorry. That's one we're gonna skip because it takes time to build the LEDs and we don't have quite enough time for that. So roaming with whiskers on page 158.
Okay.
Roaming with whiskers. And then for that one, you'll go ahead and load the code and then unplug the USB and then try setting it on the floor and have it run into your hand. Like have your, first of all, test with your hand just to make sure that when it runs into it, it'll back up and turn away. So again, for those of you who can take a minute to look up, it's very important to run the test code that that is named display whisker states, I believe. Is that what I said?
Yes.
Yeah, but I got the code up and I load it, but the screen doesn't show up. And then actually it moves.
Go ahead.
It sort of turns a few micro turns. It doesn't, it's actually driving. It's not,
so
it's not,
if you press and release the reset button, is that the micro turn that you see?
Yeah.
Okay, so that is just a twitch that it always does at the beginning of the program. The thing that we're wanting to do though is open the serial monitor. Do you have the which programming environment are you in?
Okay, so I think I've got the Arduino. We had to it's not the IDE, it's the other one. It's the Arduino
Code vendor.
1.813 or where is that? Where remember I had that issue where I couldn't
Oh, do you have Code Vendor? Do you have the web one?
I was using that on Monday. No, I was able to load it was like plan C. We had plan A.
Oh, yeah. So that should be similar to what I have up on the screen now.
Yeah, let me look.
It's not quite the same number, but it ought to be close.
Yeah, I have those codes. Yeah. So I have that. That's what I see, but I don't see the part like what it doesn't tell me the states. I don't.
Yeah, so try see the magnifying glass on the right.
Uh-huh.
Click that.
Okay. All right.
And that should bring up your, have you got it now?
Okay, yeah, I see it now. Okay.
Perfect. That is the serial monitor.
Okay, so and you're saying if they're both touching, then you get a 1-1?
If neither are touching, you get a 1-1.
Oh, okay.
Yeah, the technical name for these switches are active low, meaning that when you've pressed the switch, the signal goes low. And that, by the way, is because the chassis is grounded as in connected to the negative terminal of the battery pack. And that means that each of these metal posts that's holding a whisker is also grounded. So the voltage here, these resistors here, oh, I'm getting ahead of myself. I have a slide for that. But at any rate, yeah, we're grounding out that pin is being pulled up to 5 volts when the whiskers aren't pressed. And when you press the whisker, it shorts those 3-pin headers to ground in a constructive way. And that's how you get the 0 as a result of the contact.
All right. Well, they're successful.
Perfect. So you are ready to move on to the navigation sketch, which its name is Roaming with Whiskers. Chapter 5, Roaming with Whiskers. Oh, one very important thing is you want to close that serial monitor. Okay, so before you try to load or before you open another program, close the serial monitor. and then go find roaming with whiskers. And you can load that and then set it down on the floor and try pressing each whisker and verify that the robot backs up, turns, and goes another direction.
Hey, Andy, can we ask a question? There's another Andy who and I are having the same exact problem.
Okay.
Where if you run it with the USB cable and everything's fine, as soon as you unplug the USB cable, it like restarts every time the whiskers touch.
Okay, so that usually, so were the wheels turning and then as soon as you press the whisker, it restarted?
Yeah.
Low batteries.
Oh, no way.
Yeah, and that's actually one of the reasons that we put the speaker on is so that the speaker makes a tone each time the program begins. And if the batteries tank, the Arduino protects itself by shutting itself down. It has a brownout detection circuit on it. And when the battery voltage tanks, because it has to supply a bunch of energies to the servos to force a change in direction, that's when the voltage tanks, the Arduino shuts down. When it wakes back up, it starts over at the beginning of the program, making a speaker beep.
Thank you.
You are welcome. That's somewhere in the book. I don't remember where, but it is. But we do make a to-do of it, and thanks for helping demonstrate that, because otherwise I might have forgotten to tell you about it.
You know, Andy, you keep referencing that slideshow. Was that sent out at one point that maybe I missed?
Maybe. Let me paste you the link. And see here. So I am on slide 69. And once you get here, slide 4 has all kinds of other great links too. Let's see. Where's the chat? Here we go. And is this to everybody? No, I'm on one person. Send chat to everyone. Paste. Okay, there is a link to the slideshow.
Great, thank you.
You are welcome. One note about the slideshow is I repeat a number of slides whenever I review or talk about stuff. So you will see a considerable amount of repetition in the slides. Because there's a number of spots where instead of trying to jump back to slide X, we just copy and paste slide X in the sequence.
So I don't know, did you say this already, that every time we change circuits and add resistors, we're supposed to unplug everything?
I mentioned it kind of after I started playing with one of the circuits. It's really okay. This is fairly robust. It's a good habit to get the students into, but it's very unlikely to do any damage.
Right. So, and then the programming plug, that kind of goes in tight and out. If kids are taking it in and out a lot, would it end up getting damaged?
Not normally, especially if you used there's a pair of screws that we did some fumbling with that holds the Arduino in place up against the shield. Screws and nylon spacers from day one. When those are used, it makes it a little bit more durable, a little bit less likely to try to come undone. Otherwise, without those screws, let me see if I can find the slide for that. So I'm going to come back to 72.
I think it's important though, Andy, that the students realize that the wire, pulling on the wire is not the disconnection point. You know,
oh yeah, that's a good
what
point,
they're
Ed.
used to
Thank
with their
you.
Phones or, you know, unplugging from the wall. Why not jerk the power cord? And I think that's the only way you'll damage this connector.
Yeah. So the connector, it's kind of hard to damage, but there was some screws and spacers. The thing that I'm always concerned about having damaged is if you don't use these screws and spacers, it puts a lot of stress on these pins that hold the Arduino underneath the shield. And so my main concern is just making sure to get these screws holding the Arduino in place so that when you unplug and plug the serial cable, the USB cable, pardon me, that that there's not stress placed on these pins that are sticking out. So that's an important, really, I think an important consideration. Just wanted to point out, remember I talked about having forward, left, right, and backward functions that would be used later in the book. Well, here we are later in the book. So this is what we use for whisker navigation. Can I get thumbs up just on the screen? You guys got it to go? All right, good job, people. Excellent. All right, quick how it works. Back to the light emitting diode. To make a light go on, you have to give it some DC voltage, like putting connecting its ends to opposite ends of the battery, the plus and minus terminal, that forces current through. Whereas if you plugged both of them to the negative terminal of the battery, there's no voltage difference, so there's no pressure to push those electrons through, no current, no light. And I'm going back to something that we kind of skipped in the interest of time, but I'm hoping you guys are okay with this. Basically connecting a light and turning it on and off. The students will do that considerably before they center their servos. And so they'll be very familiar with turning the light on and off. And they'll know that digital write 12 high will make a LED light connected to P12 turn on, and that digital write 12 low will make it turn off. Well, one of the things that the book explains is that in order to do that, the microcontroller itself essentially connects the P12 pin to its 5-volt supply through transistors inside the chip. And then digital write 13 low or digital write 12 low, whoopsie, gonna have to go in and fix that. Digital write pin low will take that pin, and the transistors inside the microcontroller will connect it to ground, the negative terminal of the battery. And that'll, because of the fact that the other end of the circuit is connected to ground, there's no pressure, no current, no light. So the thing the main takeaway here is just to understand that you're programmatically changing the circuit by telling the Arduino, you're telling the Arduino programmatically to make changes in the circuit that make the light go on and off. Now with a sensor circuit, like the whisker circuit, it's the reverse. Instead of being in output mode, see the pin mode 12 output there, we're in input mode. In see if it says it specifically. Yeah, pin mode 7 input, pin mode 5 input. And then this is where it's checking the whiskers and calling if various functions depending on whether we had 1, 1, 0, 1, etc. So the important thing to keep in mind is that when a pin is set to input, that means it's listening. That means it's not connecting it to the positive or, to the 5 volt or ground supply. It means that for all intents and purposes, the Arduino is invisible to the circuit. The circuit is just doing whatever it does, following the rules of electricity. And the Arduino is quietly listening. And when it sees 5 volts at the IO pin, it stores a 1. And we saw that in the terminal. When it sees 0 volts at the IO pin, because we push the whisker against the post, it sees a 0 there, and it tells us that. And it does so because of digital read 5 and digital read 7 here in the whisker navigation program. Really like to add that to this slide. So that's how it's responding. It's responding with either a 1 if you have not pushed the whisker, or a 0 if you have pushed the whisker. And again, it's because that's the way this circuit behaves, is it applies 5 volts when the whisker contact is not made, and then it applies 0 volts when the whisker contact is made. That results in a binary 1 or a binary 0. Oh, here it is. Digital read 7 returns 1 and returns 0. Pardon me. So that's it for whiskers. How are we doing?
Andy, if you could go forward 1 slide.
This guy?
Nope. The other you had up with the, maybe it's back 2 with the code. That one.
Yep. There we go.
Yeah. So one thing that is important to note here for if people are they're writing their own programs, is that once you start using delay times, and if those delay times are long enough, you won't get back to that digital read very often. And so you can actually get hung up where you're driving forward or going to the right and not actually sense those pins.
Andy, what Andy points out is very important. And so let's talk about that for a second. Here is our main loop in the center. And when both are 0, we back up and then we turn left for 800. And so it's not listening to the whiskers here, presumably because backing and turning won't cause the robot to encounter an obstacle. That's not always true, but in a controlled test type of way that the class is verifying its behavior, it works. Now, if just the left whisker is pressed, then it backs up for a second and turns right for 0.4 of a second. If the right whisker is pressed, it turns left, it backs up and then turns left for 0.4 of a second. Now, there's also an else here, and that else is for when no whiskers are pressed, and you saw 1, 1 on the display. And notice that it only goes forward for 20 milliseconds. So forward 20 milliseconds, 20 milliseconds pops in here, sets it forward, the signal to make the wheels go forward, and then it just delays for 20 milliseconds before jumping back into check again. And that's how this particular example takes care of what Andy's talking about. But yes, students can end up doing stuff or taking a long time with other sensors, or maybe stopping to play some music, but letting the servos continue to turn. And in that case, yes, you could see the robot go and push against the wall because they're spending a couple of seconds doing something, as opposed to just the recommended 20 milliseconds. Thank you, Andy. By the way, I grew up in Milwaukee. I've driven through Madison from time to time. Wanted to stop at the lakes, but never got the chance. We were always on our way to McGregor, Iowa on the Mississippi at the lower corner of Wisconsin. All right, so for your homework, I would like most of you to try the infrared object detection circuit, and we'll, as needed, troubleshoot that at the beginning of the next session. So a little bit about the infrared circuit. old school TV remotes and televisions use infrared, which is a light that's not visible to us, but is highly visible to electronics. And so we have a clear LED in the kit that's an infrared LED, and it's the same thing as in the old TV remotes. So when you press a button, it sends these little flashing infrared bursts. It flashes at 38,000 times a second. They last usually a millisecond or half a millisecond, something like that, depending on whether they're transmitting binary 0 or binary 1. And that's what a infrared receiver inside the television gets. Well, and one cool thing is under your document camera, you can take an infrared remote in many cases and point it at the document camera. And when you press on the remote, you can actually see the LED light come on. It's kind of a cool thing. The students get really interested in that. You point it at the students and press the button and they can't see any light. And then you put it under the document cam and it's quite bright. Provided it doesn't have an optical filter, like many iPhones optically filter out infrared. And so you can't see it, but my old Android phone, you can see it very clearly. So using this on a robot is kind of neat because you can make that infrared LED from the remote shine out its infrared light. And if it bounces off an object and comes back to the infrared receiver you'd normally find in a television set, then it'll actually send a 0, just like the whisker did. Otherwise, if the infrared is just going off infinitely into space, the infrared receiver sends the Arduino a 1, just like the whisker did. It's another active low device. And so what you'll be doing is you're going to find the infrared LED and be very careful. I have a picture of an infrared LED and a photo transistor here. They are both clear devices, but only one of them is the infrared LED, and it has a dome top. It's clear and has a dome top, whereas the photo transistor is clear and it has a shallower dome top that's almost flat. So be careful, avoid the photo transistor, use the infrared LED. And what you'll do is you'll put it inside the black sleeve and push it in, and then you'll snap the lid of that black sleeve on it. This is the LED shield. Oh, I forget the names of it actually. The standoff is the base and the shield is the top. So you'll snap the shield onto the standoff with the infrared LED in there, and then you'll be ready to mount it on your robot. You'll need to be careful of your longer leads. Those are the anode leads. Let's see here. I'll want to call that out. Let's see here. The anode is the longer plus lead. That should be on the slide too. Sorry about that. I'll make sure to try to do something about that. So longer lead where it says anode, and we'll have you build up this circuit, and you'll want to test it. What we're doing is we're testing first, test IR left, and then we'll go back and test IR right. And what you want to do is you want to put an obstacle in front of the left flashlight, the left infrared LED right here, 6 inches away, and you'll want to see the serial monitor go from showing you 1s to showing you 0s. Does that make sense so far? So you're going to build up the circuit, and many of you, it's a more complex circuit here. So be very careful. Try to use the PDF version of the book and zoom it in so it fills your whole computer screen. That way you'll have all the color codes, and you'll have all the nice circles and arrows, and you'll be able to check each row and make sure you didn't make a mistake. And then, but we all do make mistakes, and so that's where the testing comes in. And so this is the test for the left IR, and then there's also going to be a test for the right IR. And there's also one more test where you're just checking to make sure that the fluorescent lights in your office don't happen to be flooding with infrared information that's flickering at 38 kilohertz, because that's what these receivers are attuned to. And they're only supposed to see that when you send the infrared out and it bounces off something and comes back. But again, some fluorescent lights, the ballast in those causes the light to flicker at that rate. It even makes a sound at that rate, and it's kind of thrown monkey wrenches into sonar, or I'm sorry, ultrasonic object detection as well. Remember on Monday, there was a little video clip of one robot following another? Well, it turns out that the same circuit can do a whole bunch of things. It can avoid a bold black electrical tape stripe on a piece of poster board. It can avoid an obstacle without touching it, or it can even use distance and basic proportional control for those of you who teach engineering to maintain a distance from itself and an object in front of it, provided that you're very careful about using these red, black, red resistors connected to the LEDs. If you happen to swap these and use the red, red, brown, you'll have a much brighter light over here than over here. This will be super sensitive, and it won't follow very well. So you'll be running this test for distances as well. And so this is what it looks like with the distances. There'll be a lot of noise in the distance measurements, but it'll average out to, like in this case, it's averaging out to around 3. We got 3, 2, some 4s, so 3, 4. So, and then this one's actually averaging a little closer to 3. And that's fine to have some inconsistencies, but basically if you have an object that, say, I don't know, it might be a foot away, and then you move it back an inch or two, you might want to see these change to 4s, and you move it forward an inch or two, you might want to see them change to 2s. And again, that's on the average. And if you get that to work at home, definitely go ahead and try the next thing, which is make the robot follow, and then just use your hand to lead it around. You don't need a second bot. If any of you, if the infrared detection scheme is old hat for you, another thing you could try is the light following application. That's where we shined a flashlight in front of this and then used it to lead it around. This is the light sensor circuit. Also, if you're feeling really timid about circuits, this circuit is easier to build and troubleshoot. But in terms of the code and the algorithms underneath, to make it respond uniformly to a variety of possible room brightnesses, took a significant amount of code. So the code is a little bit intimidating. So again, this is the light sensor. So now we do want the one that has kind of a flat top, as opposed to the one that kind of has the dome top. And I think we skip about halfway into the chapter to build this particular circuit. And again, I'll send you, there'll be a list of pages to go from. And you'll be using the serial monitor again, this time to detect where you are in terms of percent shade on the left and on the right. So like here, we're right in the middle. Both are about the same value. Here, the right is much shadier than the left. Here, the left is, I'm not sure why. Oh, okay, sorry. Here, the right is much shadier than the left. Here, the left has 5 digits, the right has 4 digits. The left is much shadier than the right, and then we're kind of back to normal here. And so this is something to do, cast shade over each of the photo transistors. Oh, I should have waited. here's the example, and then what happens is whichever photo transistor is shadier, we add, I believe we subtract it from the other wheel's speed, and that has it respond to bright light. And you can swap that if you want it to respond and chase after shade instead, and the book takes you through that. So for homework, there will be a video link I send you, which talks about some curriculum. We'll talk about more on Friday. Then we've got our either infrared detection or light, depending on which one you want to try. I do recommend the infrared, especially if you want to show this to your colleagues after the class. It's definitely the coolest one to have the infrared following going on. So that's a consideration. Of course, I won't argue with you doing both. So, but I think that you'll want to finish with the infrared detection. There's a PD activities document, and I'll send you a link to that. I don't know why the slide just jumped. And so here in the slide is what I'll copy and paste into an email. So this is the pages where you can go through the checklist instructions and find out which programs are used for testing and then for roaming, and then which program is used for testing the distance, and then which is used for roaming. And then here it is also for light. And then, and so again, there's a short curriculum tour video, and then we'll talk more curriculum on Friday. And we'll also talk about some of the science, electronics, and math lessons that are underneath both the infrared detection and the light following. Oh, and engineering on, most importantly, engineering to me, on Friday. Friday also, let's see, more curriculum tour. Any questions you might have thought of in the meantime on whisker navigation? Again, as I mentioned, we'll be diving into the infrared and light and some of the science underneath it. I'm also gonna take a look at some of the other lessons that are built in that I glossed over. As time permits, we'll look at some other apps that are available to you that are posted on the website, as well as kits and packages. And then we'll have some final questions and answers, and then we'll be ready to wrap it up on Friday. So how's that sound, everyone?
Sounds good.
Good deal.
That sounds good.
Okay, so
follow-on question to what I was talking about before with the, delays are bad, and don't use delays in your code because you get tied up.
Gotcha.
The ActivityBot 360, that's using the Parallax processor, which is multi-core. So
yes.
In it, I think 8 cores in that one?
Yes, yeah, it's an 8-core processor. Each one can run at 80 megahertz, and it's 32-bit processor. So it's kind of a big deal compared to, say, the Arduino, which has one 8-bit processor running at, gosh, I forget whether it's effectively, I think it's 20 megahertz, but I might be off on that.
16.
I think
thank you for the corrections.
Uno is 16 megahertz.
Okay.
So my question is if you're using the ActivityBot 360 and you have those multiple cores, you don't really need to worry about doing delays because you can have another core process each of the whiskers, right?
Yeah, I have to tell you, I was so excited to start working on the ActivityBot 360 because of that fact. Now, that said, the Arduino does use interrupt service routines to do some things for you in the background. Yes. One example is simply the servo operations. There's no code in here where we're going and manually updating the signal to the servo at 50 times a second. That's happening for us by simply declaring servo objects at the beginning, and then using the write microseconds method to tell it, oh, you've been sending it at 50 times a second, but I want you to send a different pulse width for 50 times a second. And it just keeps on doing that until we tell it otherwise. And so that is done by multitasking as opposed to multiprocessing. And I threw out the term interrupt service routine earlier. That's what's happening under the hood, is that basically a certain number of times a second, it's checking to see if it needs to send that every 50th of a second pulse to keep the servo on track with what it's doing. So that's multitasking. and it does work similarly from the coding standpoint to multiprocessing. It's just that with multiprocessing, yeah, you can have basically processors that are watching sensors that are very slow to respond, but it doesn't get in the way of rapidly detecting that whisker contact, which can be happening in a different processor. Did I get your answer properly there, Andy?
Yep. Yeah. So
Okay,
I'm
good.
actually coming at this from the opposite direction in that in my college course that I teach, we're using the ActivityBot 360.
Okay.
And we're using it. What's the online visual coding?
Oh, the Blockly prop. Yes.
Yeah. So we're using the Blockly prop. And then we actually go after a couple weeks in Blockly prop, we look at the backside of the C and I start teaching them C.
Excellent.
And then we move over to Arduino.
Okay.
And we don't even touch the robot in Arduino. So I'm trying to figure out, is there a good way for me to incorporate the Arduino robot and bring the curriculum together?
Yeah, well, that's that. I mean, you can really take it either direction because you can do there's the Venn diagram, the crossover of how much you can do with the Arduino and the propeller is pretty, those circles are pretty close together. True, you can do somewhat larger programs with the propeller and you can do somewhat more demanding tasks. And also there's an advantage to having two different processors and doing projects with them and even challenging the students to say, okay, well, you did it on the propeller, now do it on the Arduino or vice versa. Especially if it's not published, it's good to have something that they can really do and succeed at as a true project.
Good. Yeah. That answers.
Yeah. Keep going. So that answered your question.
Yeah, I just was curious because we haven't gotten into the back end and wrote C directly to the activity bots in my class. We've basically been working in the Blockly prop, looking at the C that's generated, and then they start learning C language. Then we go over and we start just like purely coding with an Arduino sitting on nothing, no motors. It's just the Arduino Uno.
Yep.
Okay. Is the course supposed to teach programming or is it teaching embedded processing?
We have two different departments that all of our instructors teach in, and one's electronics for the service technicians, and then we have one that's an associate's degree that goes into a transfer program to Milwaukee School of Engineering, MSOE.
Okay.
And so they have a different track. So the ones that are going off to a four-year institution, they don't even play with robots. They just go straight down into learning a C language, and then they learn microprocessors through embedded programming. This class that I'm teaching is more for the electronic service technician people. So it's more of a hands-on approach to it.
Yeah, because I have a similar, we call it ELT, electrical technician program. It's a 2-year terminal degree. And then they have the ENS, which is engineering science, which is the first 2 years of a 4-year degree.
Where are you located?
Long Island.
Long Island, okay.
Suffolk County.
Okay.
So because of the companies, they wanted us to teach as low level as possible because they're doing embedded processing into all sorts of things, avionics, instrumentation. So we actually have to teach them assembly level and then C.
Okay.
For the ELT guys, the engineering guys, they're at C++ and Python.
Yep. And we're moving that direction too, it seems like. We have a lot of requests for Python in our area, and not so much assembly because the compilers have gotten so good that there's not a lot of use for assembly as much anymore. A very, very small market segment. So we haven't gotten a lot of demand for that in our area. And it is very localized. Like, we've got a lot of biomed in our area. GE Medical's big here. So But there are definitely a divide between the students, and that these guys that I'm working with, they don't do any bit shifting. They don't do any registry entry. It's all just, you know, upper level functions in Arduino.
Yeah. So, yeah,
So
it's a
I'm-
simple thing. We're probably moving away from the assembly at long run. But I don't want to get into C++ at such a high level that they forget the hardware because of the problems that you're, you know, just dealing with.
Right.
You know, all
Yeah,
these,
and like the Blockly prop shows the C that it generates, your C development system will allow you to look at the assembly it generates as well.
Mhm.
For those of you who are experiencing requests for Python, our Cyberbot robot, I don't have a larger than life picture right here, but this is all Python stuff. So for example, here is computer microbit talk, which is a terminal Python. So here's the Python code going into the microbit. And then here's the Python code that goes to the microbit. And then here
What's the
is
processor used on the microbit?
the microbit is a Nordic semiconductor system on a chip that is it's a Bluetooth entity. There's a second one that all it does really is make itself look like a flash drive for the computer, which allows it so that you don't have to install any software, you don't have to install any drivers. It just works because it looks like a flash drive.
Can I
So
take off of that real fast and ask just a not so smarter than everybody else's question? I have
yeah, please.
I have a large number of the shield bots, and while we're talking about these microbits, I do have about 50 of these microbits as well. And I was wondering if there was if I could buy a shield converter to be able to use the base of these cyberbots, or sorry, the base of these shield bots to the cyberbots, and just sort of have some flexibility in switching platforms around for my ninth graders.
Yes, absolutely. The Bobot, the Shield bot, and the Cyberbot, which is the microbit robot, all have simple and not very expensive conversion kits, because for the most part, they're all basically the same. So let's see here. Cyberbot. So if you have shield bots, all you need is this board right here. If you have shield bots and you already have microbits, this board will allow you to convert a shield bot to a cyberbot.
What does that say, 69? Okay.
Yeah. And then I don't know, I'm assuming we have classroom discounts. I'm calling it up to see if because normally for the classroom, we put in quantity breaks. Yeah, so it's down to 62 at 20 plus.
All right, that sounds like a thing to go hit the CTE department up before.
Now, we also have a number of other variations, like some folks don't have the microbit. So we've got the full conversion kit that has, everything you need. Oh, you know what? Let me see. Yeah, you might need like these acorn nuts, and better make a note to myself to find out about that. Oh, here we go. Here's the extra hardware pack. So these acorn nuts, nylon nuts, and screws are used to attach the microbit to the Cyberbot board.
Cyberbot, yeah. And then one last one with the infrared, or the LED that we're doing, this infrared detector,
Yeah.
will it also be something that you could, if I had a couple of robots running around and it tried to smash into one of the other robots, would the IR be able to reassign it to a distance instead of attract it, detract it?
Yeah, you've got quite a bit of control over the code, whether you want to. Now, it's hard with robots. That's why I give them skirts, so to speak.
Yeah, I saw that.
Yeah.
I also have a ping, and I was wondering how that thing was going to fit into this whole deal as well.
Yeah, the ping is pretty good because its energy distributes well enough that it's going to hit the robot in a more, you'll get a more definite result from the ping. With the infrared, if it just kind of like, if it happens to go between the chassis and the board,
yeah,
you might not really have much detection except for off of these posts.
Yeah, I was thinking of, I was just brainstorming that, and I was thinking of 3D printing some more refined skirt.
Yes.
Than what you have, and I would just use those posts that are sitting there and just clip in some white reflective PLA or something. So yeah.
Yeah, that would be a really cool project for the students.
That's right. That's exactly what, because I'm doing a summer camp and trying to plan myself. So
okay, great.
My hopes. Thank you. I didn't mean to hijack anything. My bad.
No, I think it's great. I mean, these are questions and answers that are super important. So I encourage you and everyone else to just hit me up with those questions and answers. Although we are at about 4:15, so I'm going to, I think it's a good time to stop the recording. I don't want anybody to miss any of these answered questions though. So anybody else got something in mind?
I have something a little random.
Okay.
Do you have anything in the book that deals with the Pixie camera?
There is web documentation for that.
Okay.
So the Pixie camera, for those of you who are curious, is a really cool camera application. See if I can get it just with a search for Pixie. That didn't work out so well. Let's see. I think I have a link in the slideshow. That's right. Pixie Cam. So this is on learn.parallax.com below the main book. So if we go to the closing pages, simply because my computer's slowing down a bit here. We go back to learn.parallax.com. And yeah, so the Cyberbot is just a Python version of all this that we went over in the Arduino. And there are some YouTube presentations. We've got YouTube recordings of probably the last 4 Cyberbot courses. I could send you links to what I think is the best one of those. Arduino ShieldBot. I'm at learn.parallax.com and I chose ShieldBot. And so this is the main book. And then below that, we've got projects. And so here is the Pixie Cam. And I've got one really fun thing to show you. So this is basically the web book, booklet, I should say, for the Pixie Cam, step by step. And on the Pixie Cam note, it's just too cool. It is an activity bot video as opposed to a shield bot video, but it's very similar in terms of the end result. Stealing all my thunder for Friday.
I'm sorry.
Oh no, that's okay. And actually, it turns out that I somehow managed to not. I'm glad you brought this to my attention. We'll have to wait till Friday. I'll show you the video then. More questions, please. All right, I'm going to go ahead and stop the recording then, and I will look forward to seeing you all Friday at 2 p.m. Pacific time.
Andy, I do have a question. It may not bother everyone else, so I was trying to wait and it didn't need to be recorded.
Okay, here, let me finish this then.
Sure.
We'll go ahead and stop record. Well, how about if I pause and then repeat myself that we will see you all Friday at 2 p.m. Pacific time. And thank you for coming. And I am now ending the recording part, but not shutting down. Stop recording. Here we go.